The human brain is a massive, asynchronous engine. Right now, billions of your neurons are firing in isolated clusters, processing the temperature of the room, the pressure of your chair, and the ambient noise outside, all simultaneously and completely independently. Yet your subjective experience of reality does not feel like a billion parallel processes. It feels like a single, continuous, highly focused stream. You have one thought at a time, followed strictly by the next. This presents a severe architectural paradox. If sensory inputs are an infinite parallel flood of data, the system must compress all that noise into a strictly capacity-limited, single-file line of conscious attention. The anatomical constraints of biology make this even harder. The brain lacks dense point-to-point wiring that connects every specialized module to every other module. There is no physical center where all the wires meet to synthesize a decision. Because there is no single physical location for consciousness, it cannot be a fixed structure. Instead, it operates as a dynamic routing protocol, a mechanism capable of passing information across a distributed network on the fly. Cognitive neuroscientists Stanislas Dehaene and Jean-Pierre Changzhou formulated a model to explain exactly how this protocol works, the global neuronal workspace. This diagram maps out a bow tie architecture. Notice the clusters of localized processors on the outer edges, representing functions like perception and memory, surrounding a highly constrained hub. The thick arrows demonstrate how these outer modules drive data inward toward the central bottleneck. We are going to construct this global workspace mathematically from the ground up. To do this, we will model the different regions of the brain as extended Hopfield networks. By building these equations, we will mechanically prove how entirely unconscious parallel inputs compete to trigger the specific physical phenomenon we call conscious ignition. We can strip away psychological metaphors like a theater of the mind to understand cognition. What remains is a rigorous, computable blueprint for brain architecture. We start our construction at the bottom. We define isolated sensory areas as M local modules, operating as Hopfield networks. Inside Module M, a weight matrix encodes sensory memories by strengthening connections between internal nodes. But Module M is not alone. Visual, auditory, and tactile networks run simultaneously, generating a massive flood of data. To evaluate this data, the system calculates a variable called AM of T. This represents the average activation energy of a single module at any given millisecond. If every active module passed its signal upward, the system would immediately overload. To prevent this, the network relies on a lateral competition parameter, denoted by the Greek letter alpha. Alpha dictates the strength of lateral inhibition. Mathematically, a highly active module uses this parameter to project a dampening signal outward, actively subtracting from the activation scores of its neighbors. Only the mathematically loudest signal survives as continuous cross-suppression, granting that specific sensory data priority access to the next layer of the architecture. Here is the central hub, the global workspace, a centralized Hopfield network positioned above the sensory modules. Surviving signals travel upward along these pathways, mapped by connection matrix CWM, dictating physical routing from local modules into the hub. The workspace computes its total aggregated input using an equation called IU of T. Crucially, this equation only aggregates signals that successfully defeated their neighbors during the lateral competition phase. Once the data uploads via the connection matrix, it collides with the workspace's own internal weight matrix, JW, which evaluates how this new input aligns with the network's global memories. The central nodes then execute a state update, calculated as y of t plus delta t. The central network recalculates its entire configuration to absorb the new aggregated input, forcing thousands of parallel sensory streams to compete for entry into this single low-dimensional matrix, mechanically generates the strict capacity limits of human attention. The transition from unconscious processing to conscious awareness relies on a strict mathematical threshold in the network, denoted as theta.
We monitor the average activation of the entire workspace layer, called AY of T. When this average remains strictly below theta, the signals are processed, but they stay entirely latent. The network is working, but you are not subjectively aware of it. This data visualization plots average workspace activation over time. Watch what happens when a sensory signal pushes the average across the theta threshold. Instantly, a nonlinear phase transition occurs. The central network collapses into a single global attractor, silencing background noise. This system-wide collapse is conscious ignition. Operating as an all-or-none event, the signal does not gradually fade into view, it instantly synchronizes the entire hub. This phase transition into a stable global attractor is the physical mechanism of subjective experience. That vertical spike is a thought entering your mind. Maintaining a conscious state is biologically expensive. Simply holding an abstract representation in the central hub serves no evolutionary purpose unless that state can coordinate the body to act. To drive action, the workspace utilizes FIW, the feedback matrix. Represented by the downward arrows, this matrix allows the central hub to actively broadcast the ignited conscious state back down to the specialized processors. This top-down broadcast physically alters the local energy fields within the unconscious modules. By changing their baseline parameters, the workspace shifts the attention and priorities of the very systems that feed it. To be effective, the network must also learn from the decisions it broadcasts. This requires updating the workspace memories, governed by this Hebbian plasticity equation. Notice the y of t plus delta t terms highlighted here. The equation calculates changes based upon a forward time projection. The network adjusts its synaptic weights based on the resulting dynamic state it achieved, rather than anchoring to its past state. This synaptic plasticity permanently imprints the conscious event into the architecture, ensuring that future identical inputs trigger a faster and more efficient path to ignition. The biological algorithm is a continuous loop. An isolated sensory input suppresses its neighbors, routes upward, and breaches the threshold to trigger a system-wide ignition, and then broadcasts that global state back down to drive physical behavior. This loop resolves the paradox we started with. A massively parallel set of processors generates perfectly coordinated serial decisions by routing all signals through a highly constrained competitive bottleneck. If the central threshold cannot be breached, or if the connections are chemically blocked, local modules continue firing, but global synchronization fails completely. We observe this disabled routing state in human biology every day. It's the neurological signature of deep sleep and the exact mechanism of medical anesthesia. The global neuronal workspace operates computationally as a high-level RAM. It is a temporary, globally accessible registry that integrates disjointed expert systems into a unified agent. Understanding the mathematics of human consciousness provides a direct framework for engineering artificial cognitive architectures. Instead of basic binary models, engineers can integrate modern Hopfield networks into the central workspace layer of an AI agent. Modern Hopfield networks utilize continuous state energy minimization with non-polynomial interactions. This yields an exponential memory storage capacity compared to classical models, allowing the central hub to manage immensely complex global states. For the local sensory nodes, the standard update equations can be replaced by liquid time constant neural ODEs. Liquid neural networks address their effective time constants dynamically based on the exact inputs they receive. This grants the localized modules the ability to fluidly adapt their processing speed to real-time environmental changes. By combining the global neuronal workspace routing protocol with the capacity of modern Hopfield networks and the adaptability of liquid neural ODEs, we discard philosophical metaphors of the mind, leaving us with a rigorous mathematical blueprint for fully autonomous, self-repairing agentic systems.